Today we will present our study on the configuration-dependent oxygen reduction reaction performance of pyridine decorated NIPT nanocrystallized. This is the outline. Introduction. In fuel cells, the major bottleneck is the cathotic oxygen reduction reaction OR. Since OR is the neutral step process, it causes the largest overall potential loss of about 0.3 to 0.4 volts, and therefore largely determine the fuel cell's performance. PD is the benchmark OR crystallized, but it suffers from degradation, unfavorable intermediate absorption behavior, fuel crossover carbon dioxide poisoning, and scarcity. This limitation drives the development of PT-free cholestasis. PD is the key alternative because it is PD-like, more abundant, and more CO tolerant. However, its OR activity is still behind that of PT. In this work, the main strategy is to introduce atomic scale in iridium clusters on palladium nanoparticles and support them on a tetrahedral nickel oxide support. The author emphasized that by only slightly changing the impregnation temperature during nickel crystal growth, 25, 40, and 70 degrees Celsius, they can significantly tune the configuration, leading to large difference in OR performance, even with similar compositions. For the method, first, the carbon support is treated. Carbon black is SC treated in 4.0 molar sulfuric acid at 80 degrees Celsius for 4 hours. Wash to a pH of about 6, forming functionalized active carbon, and then prepared as a 3 red percent depression. In step 1, nickel ion impregnation and nickel crystal growth are controlled. A 0.1 molar nickel colloid solution is mixed with the active carbon depression and stir for 4 hours in 25, 40, or 70 degrees Celsius. This temperature is key variable in the entire period. In step 2, rapid sodium borohydride reduction forms nickel nanoparticles, which partially oxidize to nickel and nickel oxide. After that, the equimolar palladium precursor solution is added, allowing palladium nanoparticles to grow on the NiOX ports. This product is referred to as MP. Finally, iridium clusters are decorated. The MP samples is first ultrasonicated to create defect site. Then an iridium precursor is added and reduced by sodium borohydride to anchor atomic iridium clusters on the surface. After washing and drying at the 70 degrees Celsius, the samples are named MPI-RT, MPI-40, and MPI-70. According to the nickel impregnation temperature, an iridium-free control prepared at 40 degrees and denoted as MP40. Electrochemical OR tests are carried out in 0.1 molar potassium hydroxide using the rotating disk electrode. Catalyzed inks is prepared by depressing 5 milligrams of catalysis in IPA with naphthalene. Cyclic voltammetry is measured under nitrogen. Linus voltammetry under oxygen at 1600 RPM, and durability evaluated by an accelerated durability test ADT.
In this slide, we'll explain the STM image and EDS elemental map of the NPI nanocrystal that prepared at the different impregnation of the temperature. For the NPI-RT, which prepared at the room temperature, the Ni atom will be migrate slowly during the synthesis because of the slow migration, and the Ni atom will be tend to accumulate and form the large Ni particle. This behavior can clearly observed in the figure, and when increased to the 40 degrees Celsius, the N atom become more mobile, and in the result, that will be better dispersion on the carbon supports. And in the 70 degrees Celsius, can observe that Ni atom will be highly mobile and become the atomically dispersed on the carbon support. This leads to the formation of the NIPD structure. And this slide will show the HRTM image of the NPI nanocrystal, which provide the information about the lattice structure. For the NPI-RT at the room temperature, can show that measure the d-spacing about the 0.235 of the nanometer. This value is larger than the standard of the PD, indicating the presence of the tensile strength in the lattice. And in the NPI 40 at the 40 Celsius can show that the d-spacing decreased to around the 0.223 nanometer. This will be reduced the spacing, suggests the composite strain in the PD lattice. According to the paper, this strain is related to limit the heteroatomic intermixing at the NIPD interface. And in case of the NPI 40, as in the 40 degrees Celsius, the d-spacing increase again will be changed to attribute the stronger PD replacement by IR atom, which is consistent with the EDS result showing a lower of the IR density. For the XRD analysis, in this slide, we discuss the XRD pattern of the NPI nanocrystal that will show in the figure 2. The broad peak at around the 24.5 degree will be correspond to the carbon support. The peak at the approximately around 40, 47, and 68 degree are assigned to the PD plane respectively. And the observation in RPD diffraction peak of the NPI 40 will be shifted to the higher 2 theta value will be compared with the NPI at the room temperature and NPI at the 70 degrees Celsius. And the right shift will be indicate the presence of the composite lattice in the NPI 40. These XRD results are consistent with the HRTM observation and confirm that NPI 40 has the most complex of the PD lattice structure. For the X-ray absorption near edge, we will provide the information about the local atomic and electronic structure of the NPI catalyst. At the NIKH, will show in the figure 3A. The NPI at the room temperature mainly exhibit on the octahedride of the Ni coordination. In contrast, the NPI at the 40 degrees Celsius and the NPI at the 70 degrees Celsius will show the tetrahedride of the Ni coordination. This indicates that increasing the impregnant temperature will be strongly affect the Ni crystal growth. Additionally, the NPI 40 will show a lower absorption intensity compared to the other sample. According to the paper, this suggests fewer the surface absorbed species and a higher metallic character of the Ni atom, likely due to the PD shielding. And at the IR-L3S will show in the figure 3B, the NPI at the 40 degrees Celsius exhibit the lowest white line intensity, indicate the higher occupy of the NID band.
Now I will focus on the electrochemical results starting from the cyclic photometry analysis. The CV curve were measured in nitrogen citrate 0.1 molar TKH with the scan rate of 20 million volts per second. As shown here, all catalysts exhibit 3 typical potential regions. the hydrogen under potential deposition region, the double layer region, and the oxide formation and the reduction region. Importantly, although the composition are similar, the CV profile show clear difference depending on the nickel growth temperature, indicating that the surface chemical environment is strongly structure dependent. And next, I will highlight the key CV features that explain why NPF40 performed the best. First, NPF40 shows sharp and well-defined HUPD peaks, which are a typical fingerprint of atomic scale iridium cluster on the surface. Compared with NP40, the oxide reduction peak of NPF40 shifts positively by about 45 million volts, and the oxide formation peak intensity is significantly suppressed. And this feature indicates the reduced energy barrier for oxygen absorption and dissolption. In addition, the shooter peak appears around 0.85 volts, which is attributed to oxygen dissolption occurring at the nickel palladium interface. Overall, the CV results suggest that NPF40 provides the most favorable surface chemistry for the oxygen reduction reactions. Based on the CV analysis, the OR activity was further evaluated using the linear sweep photometry. Among all samples, NPF40 exhibits the highest onset potential and halfway potential, with the value of 0.915 and 0.96 volts versus RHE respectively. This indicates that NPF40 has the lowest activation energy for ORR. And when normalized by iridium loading, NPF40 achieved an extremely high mass activity of 12,163 million amperes per milligrams of iridium at 0.85 volts, which is about 181 times higher than that of the commercial platinum carbon. In terms of durability, NPF40 shows excellent stability under accelerated degradation test. There is no performance loss up to 20,000 cycles and only a 5 million volt shift in halfway potential after 30,000 cycles. In contrast, the NP40 sample shows significant degradation after only a few thousand cycles, highlighting the critical role of iridium cluster distortion. And to conclude, the NPF40 has been the best overall performance among the own investigated catalysis. The expansional activity originates from the synergistic effect of the high occupied density of iridium d orbital and the compressive strength at a nickel palladium interface. Moreover, atomic iridium clusters significantly enhance not only the reaction kinetics but also the long-term durability. And these results demonstrate the effective strategy for designing high-performance palladium-free OR catalysis. And thank you for your attention.